Calibration and validation are often treated as routine steps, yet they are the foundation of model credibility. Done properly, they transform a theoretical model into a reliable predictive tool. Done poorly, they create false confidence. In this video, we will walk through what calibration and validation really mean and discuss the best practices, common mistakes, and troubleshooting when things don't go as expected. Stay with me. A hydrological model is essentially a mathematical representation of catchment processes. But regardless of model complexity, lumped or distributed, two steps are essential before using it for prediction. Calibration is the process of adjusting model parameters to minimize discrepancies between simulated and observed data. It is fundamentally a parameter estimation exercise where the model learns how the catchment responds to rainfall. Validation, in contrast, tests the calibrated model against independent data to assess its predictive robustness and guard against overfitting. Together, calibration and validation establish model credibility. The best practices for professional modelers are as follows. First is the data quality auditing. Before calibration starts, rainfall and runoff data must be scrutinized, because poor input data inevitably produces poor calibration. Therefore, check for gaps, anomalies, inconsistencies. And don't forget, visual inspection often reveals issues that automated checks may miss. Second is Baseflow Separation. Most rainfall runoff models simulate quick flow rather than the total stream flow. Separating baseflow or explicitly modeling it ensures consistency between simulated and observed components. Third is the data splitting strategies. Industry practice requires dividing data records into calibration and validation datasets. Different splitting approaches serve different purposes. First is the temporal split. We calibrate on the first n years of the data and validate on the remaining part. For example, a 50-50 or 70-30 split. This serves temporal transferability. Second is the magnitude split. We calibrate on small to medium events and validate on remaining large ones. This is best for testing the model extrapolation capabilities. Third is the wet-dry split. We calibrate on wet years and validate on dry ones, or vice versa. This is best for assessing structural adequacy. Finally, cross-validation. We use multiple calibration validation combinations to estimate the model uncertainties. This is best for catchments with limited data. The fourth one is sensitivity analysis. Not all parameters matter equally. Identifying a few influential parameters before calibration begins can reduce dimensionality and help us avoid equifinality. Fifth is the warm-up or spin-up period. Hydrological models have memory stored in their soil moisture and groundwater storage components. Starting simulation without stabilizing these initial states biases early results. Including a spin-up period allows the model to forget arbitrary initial conditions. The actual warm-up time required depends on the model structure, catchment wetness, and basin size. Research suggests that setting the warm-up to 5 to 7% of the total statistical period often enhances overall model efficiency. The sixth one is the sequential calibration. A structured approach improves efficiency. First, calibrate volume-related parameters such as losses. Then calibrate routing parameters, controlling hydrograph timing and shape. Seventh is the performance metrics. No single metric captures all aspects of model performance. A robust evaluation typically combines several metrics such as Nash-Sutcliffe efficiency for overall hydrograph feet, percent bias for runoff volume, peak error for flood magnitude, and time to peak error for routing representation. And importantly, always complement metrics with visual inspection. Several pitfalls repeatedly appear in practice. First is the Equifinality, which can produce good fits for the wrong reasons through parameter compensation. If you would like to know more about Equifinality and ways to avoid it, please watch our video on this topic. Second is the non-stationarity. Urbanization or climate shifts can undermine calibration transferability. Third, unrealistic parameters, which can weaken physical credibility. Fourth, incorrect timestamp selection, which can smooth peaks and distort system response. A rule of thumb in hydrological modeling suggests the simulation timestamp should not be larger than 1/5 to 1/10 of the catchment time of concentration (TC). Finally, calibration and validation overlaps. Note that calibration and validation datasets must remain independent. Even experienced modelers may encounter difficulties. If calibration fails, first revisit data quality, rainfall representation, catchment characteristics, and parameter optimization method. If calibration is good but validation is poor, check for overfitting, non-stationarity, or extrapolation beyond calibration range. If metrics look good but hydrographs appear unrealistic, remember that performance metrics can be misleading. So, inspect application-relevant metrics. And when parameters appear unrealistic, investigate parameter compensation or data inconsistencies and consider tighter parameter bounds or regularization. The quality of calibration and validation governs the model's credibility. The most reliable modeling workflows combine sound data preparation, structured calibration, multimetric evaluation, and transparent acknowledgement of uncertainty. Because in rainfall-runoff modeling, confidence is not built on a good fit alone, but on demonstrated robustness. If you found this video helpful, please share it with others and subscribe to the channel for more videos like this. Thank you for watching. I will look forward to seeing you in the next one.